Lab 3 Black Hole by Caitlin Schmidt. The introduction for part 1 of the experiment. A star is orbiting a black hole with unknown mass at the origin, and the star mass is 2.0 times 10 to the 30th power kilograms, and the goal is to analyze the star's motion and determine the net force acting on it. And we're assuming the net force on the star is only due to the black hole, and the time between the data points is 1 Earth day. The tasks are to modify the code, create simulation and GlowScript, calculate the net force of the star at every position, determine the parallel and perpendicular components of the net force, and use gravitational force to estimate the mass of the black hole. This is the introduction for part 2. A spaceship is now approaching Model 1, and there's a planet orbiting the star and a moon orbiting the planet. The goal is to place the spaceship in an orbit around the moon and the planet without it crashing. And the tasks are to modify the code to create the GlowScript simulation, determine the initial velocity, calculate all forces on the moon and the ship, and use Newton's second law and update position formula to make the moon and ship move. So these are the key principles needed, which is momentum, Newton's second law, and Newton's universal law of gravitation. These are the initial conditions for Model 1. We have the gravitational constant, the mass of the star, which we are given, and the time interval, which is 1 day, and starting the time at 0. It's the iteration part for Model 1, and basically it's a while loop with all of the key principles needed to calculate the mass of the black hole. These are the results for the computational Model 1, which includes the diagram calculated, the FNet, the FPerp, and the FPAR, the time, and the estimated mass of the black hole. Now for Model 2, and the initial conditions for Model 2, the first 2 screenshots were given to us, and the last one, which is the ship speed of both the X and Y component, I had to mess around with and basically just estimate to be able to get the ship to not crash. Here's the iteration for Model 2, which also includes a while loop and includes all of the key principles and equations needed to make sure that the ship stays in the infinity loop orbit and not crash. Results for Model 2. Unfortunately, I did not achieve a perfect infinity loop, but it was close enough for the purposes of this experiment because the ship did not crash. And it also included the moon's orbital speed and the moon's orbital period. Now for the analysis of Model 1. So the mass of the black hole should ideally remain constant throughout the experiment, but it didn't, and the calculated mass fluctuated slightly, but consistently rounded to 1.72 times 10 to the 34th power, and small deviations likely occurred because the net force was approximated at an average over each time step, so it varied slightly. This is the analysis for Model 2. The moon's orbital speed was around 2.4 times 10 to the 4th power meters per second, and the moon's orbital period was around 64.4 hours. Unfortunately, the spaceship did not orbit around the moon and planet in an infinity-shaped loop, but it was close enough for the purposes of this experiment because the ship did not crash. So what does this mean? The net force can be found from Newton's second law, and the rate of change of momentum can be directly measured by tracking how velocity changes over time and multiplying by mass. The parallel components can be observed through changes in speed, while the perpendicular components can be seen in changes in trajectory. The net force is applied to the object, while the rate of change of momentum is a response of the object's motion to the force. Net force causes changes in motion, while rate of change of momentum describes the magnitude. Now for the answers for the what if section. What we need is Newton's law of universal gravitation for all objects, the velocity and position update formulas, and iteration over the given time period. And key considerations we need to take into account are that the black hole dominates, but the star-planet system behaves like a mini-system inside the original system. Close objects experience a stronger mutual effect than the distant ones. In conclusion, the black hole's mass was determined by assuming the net force equals the gravitational force from the black hole, and the success of this maneuver depended on careful calculations of net force and momentum changes. Considering both parallel and perpendicular components, and momentum analysis helped predict how the spaceship's magnitude changed, while the net force calculations ensured the correct path was maintained.